Okay, hi guys, so we'll be continuing on seeing more on Maxwell distribution curve. So let's get started. So we actually saw two different graphs depending on the temperature for the same particular gas in the previous lecture. So just continuing on from that the total area under the curve actually remains constant, although we saw that the nature of the curve were different in the two cases. And one more observation from the previous curve, that when temperature increases, all types of speeds, whether it is VRMS, VMP or V average, all types of speeds of gas particles increases. Okay, so let's actually see the speed of gas particles, or rather let's again see the Maxwell's distribution curve, where we have fraction of molecules on y-axis and speed on x-axis. So the graph's nature would be something like, we have for oxygen we would have something like this curve, then for let's say nitrogen we would have something like this curve, and for hydrogen we would have this curve. The average, the most probable, or the RMS speed for hydrogen would be highest in all the cases. Why? Because velocity is actually inversely proportional to molar mass, root of molar mass. Okay, so this explains the reason why this is the nature of the three curves. So as the gas becomes lighter, or rather we can write that lighter gas molecules have very small fraction of slow moving particles. Okay, and we can also say that if m by t, or molar mass upon temperature, term is identical, rather is same for two gases, then the curves would of both of them would be identical, then their curves would be identical. Okay, so now actually let's discuss more on most probable speed. Or VMP. So VMP is the speed possessed by maximum fraction of gas molecules. As the name suggests, speed possessed by maximum fraction of gas molecules. For maxima, we can have that d upon du times 1 upon n dn by du should be equals to 0, and when we actually solve this equation, you can get VMP as root 2 RT upon m. Recommendation is that to directly remember the formula and don't need to derive the formula again and again in the actual examination, because the derivation is of less importance in this case. Just directly remember the formula of VMP. Okay, next let us talk about average speed. So for average speed of or VAVG would be equals to under root of 8 RT upon M. Okay, so this is nothing but arithmetic mean of different velocities possessed by gas molecules. Possessed by gas molecules. Okay, so we can write that UAVG or VAVG, whatever you want to call it, would be U1N1 plus U2N2 divided by U1 plus, or rather N1 plus N2 plus, so on. So we can also write U average or V average as integration of UdN by N, and ranging from 0 to infinity. Solving that, you can directly get 8 RT upon M as the U average. Recommendation is, again, just remember this form directly. No need to derive it again and again, but the method should be known to you. Next, let us discuss about root mean square velocity or root mean square speed. So root mean square speed would be defined as URMS, U square or V square would be U1 square plus U2 square, so on, divided by total number of, rather total N. Okay, so we can also write that U square is, so this is one of the way of writing it. We can also write that U square is U1 square N1 plus U2 square N2, so going on, divided by N1 plus N2 plus, so on. So from this we can get that URMS or VRMS is nothing but root of 3 RT upon M. Okay, so just remember this form. So in this lecture we'll discuss VRMS, V average speed, and root mean square speed. So in the next lecture we'll be continuing on seeing the same, and then we'll be seeing collisions of gas molecules as the new concept. Okay, so till then, good luck and goodbye.